Okay, I might be from here. It could be, but let's introduce. Let's start our session today, and let's introduce our speaker, Anastasia Vyalikh. If you can find it. She's going to be a speaker today. She works at Dresden University of Technology. She is a senior scientist at the Institute of Solid State and Material Physics of this institute. And she is an expert in nuclear magnetic resonance, I would say, technique. And she uses this technique to measure various states of matter, amorphous, crystalline, biological systems, and so on and so on. So I do not talk about details. She is going to present her results in detail and what her educational career and scientific career can be found in her curriculum. I do not talk about her careers here. I try to save time for her talk. Thank you.
Thank you, Eugene, very much for introducing me. And I would like to thank the IPC for inviting me and for giving me the opportunity to present my research here. So, I'm working as Eugene at Dresden University of Technology, and here just a few topics we are working on. So the structure, property, relationships in functional materials. We work also on studies of molecular dynamics and on apparent studies of electrochemical and electrocatalytical reactions. The methods we apply comprise solid-state nuclear magnetic resonance, electrical impedance spectroscopy, and quantum chemical calculations in order to support our experimental observations. And here only few systems are the study which we worked on. So they comprise organic-inorganic nanocomposite materials, biomimetic materials, ionic conductors, and carbon-based nanostructures. So in my talk, after brief introduction into the backgrounds of NMR, I'll present my research results on two topics, which are in principle connected to each other, but they best demonstrate the unique ability of NMR in such modern research fields as life science and energy research. So, in the first topic, I'll present the application of NMR on biorelevant materials, and then on the situ with slow NMR for electrochemical reaction studies. So, let's start with introduction. Nuclear magnetic resonance is a nucleus-specific spectroscopy which provides the information about the molecular and crystalline structure and dynamics. So what we need a sample which can be gas, liquid, solid, crystalline, or amorphous, but which must contain nuclear NMR active isotopes. So when we use it in NMR, so we need a magnetic field. This results to Zeeman interaction, and in the case of the phenomenon of nuclear magnetic resonance takes place, we get the spectrum which can be analyzed towards the structure or dynamics. So a little bit more details. Not all nuclei can be measured, can be observed in NMR. So if nucleus has a non-zero nucleus spin, then it poses a magnetic moment, like in the case of, for example, hydrogen isotope H1, which is called also proton. It has spin number 1/2. And if, the spins when no magnetic field is applied are randomly oriented. If you apply a magnetic field, they become aligned in a magnetic field along or in opposite direction, and we observe the Zeeman effect. So important is the distance between energy levels. In the case of proton NMR, we have two energy levels, spin or plus 1/2 minus, and this energy or the distance between energy levels is defined by Larmor equation, which is a function of a product of gyromagnetic ratio, the property of a nucleus, and strength of magnetic field. So, in order to create the resonance conditions, we need to apply the second field, which we call B1. And if this field matches the Larmor frequency, the energy will be absorbed, and we observe nuclear magnetic resonance. So in this scale of electromagnetic radiation interaction, we see where NMR is located. And for resonance conditions, we need to apply energy of field of megahertz. And we normally apply radio frequency pulse. Application of NMR extends from physics and chemistry, where we normally want to elucidate the structure, and it extends to chemistry or to biology and medicine. So in biology, normally 2- and 3-dimensional spectroscopy has been done in order to elucidate the complex structure of large molecules like proteins. And critical application of NMR is tomography, well known. So in my talk, I'll concentrate on specific applications which make demonstrate unique properties in NMR, and demonstrate that we can probe specifically interfaces using this technique, and we can use it in electrochemistry. So the first application is combined biorelevant nanocomposites. So under biorelevant materials, we understand mineralized tissues of both natural and synthetic origin. Most common or well-known mineralized tissues are bones and teeth of vertebrates, that means animals and humans, and they are all nanocomposite materials. What does it mean? So they are composed of two phases: inorganic, represented by various calcium phosphates, and by organic phase, mainly polygenic proteins. So they are mixed on a nanoscale, and therefore we call it nanocomposite materials. And the materials property of hard tissues are defined mainly by interfaces. Therefore, bone is so elastic and at the same time hard and strength. And the aim of research is to learn from nature how to build such sophisticated materials and implement this knowledge for design of artificial materials, For example, artificial bones or dental tissue, which are capable to self-healing, for example. So, and we want to concentrate on the studies of interfaces in such nanocomposites. There are different approaches, and the most common is so-called direct polarization. So we apply radio frequency pulse to certain nucleus, for example, carbon-13, and detect the spectrum of the same nucleus. So this is a direct polarization. An alternative approach is cross-polarization. We send RF pulse to, for example, proton, transfer magnetization to another nucleus, and detect the signal on the second, on the carbon. So we can vary this magnetization transfer conditions, measure different intensity spectra, and also estimate distances between these nuclear pair. Especially interesting, the interface is located exactly between these two nucleus. So this approach allows us to investigate exactly the structure of interface region. So now I'd like to present our study on synthetic biomimetic nanocomposite produced, synthesized by our colleagues from Max Planck Institute in Berlin. Why it's called biomimetic? Because we used fluoroapatite instead of hydroxyapatite, which is the most common constituent of hard tissues, and we used gelatin instead of collagen. So this is a system which is easy to produce and easy to measure. Therefore, but it somehow mimic the natural bone. This material, nanocomposite, has been studied by different characterization tools. We observed the diffraction pattern of a single crystal. But if you look at microscopy image, we see that it is not a single crystal. It has a nanocomposite structure. So here you see that material consists of nanocrystallites of nano sizes, which are elongated along the same direction. And this type of material is called mesocrystal because it's organized on the mesoscale. So it has been found that nanocrystallites consist of pure crystalline fluorapatite. And the question was, what is the phase between them? And what is the interaction which keeps two phases, crystalline and amorphous, together? What is the cohesive force? So here we were lucky to apply NMR because both phases contain NMR active isotopes. So fluorapatite, we can probe proton, fluorine 19, phosphorus 31. Gelatin has even more NMR active isotopes, but we will concentrate on the one. So we start from NMR on fluorine and apply also two approaches which I have shown before. So direct polarization and cross polarization. So if we look at the upper spectrum, we see the presence of four components. The dominant, the red one, is located at minus 103 ppm, which is a signature of fluorapatite. If you look at cross polarization, the signal disappears, and it's clear because there is no fluorine hydrogen spin pair in this structure of nanocrystallites. But instead, we see all other species which may result from, for example, amorphous component from organic phase. But this information is not sufficient. So we see we can't extract too much from 1D. Therefore, we apply two-dimensional spectroscopy and look at heteronuclear correlation, shortly called HETCOR. This spectroscopy is based on a distance-dependent dipole coupling and can emphasize spatial proximity between the two nucleus. For example, horizontal scale, we see the spectra on fluorine. On the vertical scale, measured on proton, and only those which nuclei which are close to each other will provide resonances here. So therefore, we don't observe the signal from fluorapatite, but the other can be assigned to different species based on chemical shift information. So, and if you look at phosphorus data, so we can play around with decoupling techniques, cross-polarization from different nucleus. So we see some interplay of intensities in this spectra, but again, it's not too much informative from 1D, and therefore we switch to dimensional spectroscopy. And here we also can correlate different spin pairs. On the upper spectrum, we can correlate phosphorus with fluorine and look at structures where these spins in close proximity to each other. And on the spectrum below, we correlate phosphorus and proton spectrum information. So on the upper spectrum, we see only one signal, which is signature fluorapatite. So this is a crystalline phase which we have seen on microscopy images. So in contrast, when we look to phosphorus proton correlation, this signal disappears, and instead we see all other possible structures which can be located in amorphous phase or an interface region. So, and now, based on information we got from one-dimensional spectroscopy, from two-dimensional heteronuclear correlation, we can now propose a structural model on a molecular level. Which is important. So what we see, these hexagons. So these hexagons arise from fluorapatite nanocrystallites with a gelatin bundle in the middle, which acts as crystallization agent. The phase between crystallites is amorphous layer, which contains water, organic molecules, orthophosphate groups, and some other stuff. And black circles are exactly the interface structure, which is quite thin, but based on chemical shift information from our spectra, we can now state that main interaction which keeps two phases together is a hydrogen bond interactions. So, and now we can apply this approach, we can apply our knowledge for the studies of natural systems which are more complex. We switch from modern synthetic nanocomposite to natural mineralized tissues. So, you know, the most common biomineral is calcium phosphates. So they can be different. Most frequent calcium phosphate is hydroxyapatite. when we understand the mechanisms of biomineralization which take place in natural biological environment, so we can be able to develop novel advanced materials, for example, self-healing bonds, or we can be able to treat calcified tissue diseases. There are a classical pathway of biomineralization has been revised, which was known to consist of two steps, ion association and crystallization. And recently, different approaches, biomineralization process have been proposed. They are all based on multi-step biomineralization. And here you see one of such process published a few years ago in Nature Materials. I'll not go into details here, but we see that this process consists of multiple steps. We wanted to apply NMR to prove or disprove one of such theories. So, and we performed quite complicated study in cooperation with the University Hospital in Dresden and Max Bergmann Institute. So this study was based on in vivo bone formation and ex vivo characterization. So what we did, we inserted dental implants from titanium oxide into mandibles of mini-pigs. Mandible is a jaw bone, and let it heal for different time periods, 2 weeks, 4 weeks, and 8 weeks. Then animals were scarified and pieces of bones together with the implants were extracted and studied. So, and not studied only by NMR or MRI, but also other means to reduce the trouble for animals. So on this right image, so photon density MRI, you see the black spot which results from dental implant, colored image surrounding this implant results from living tissue, and we were interested in this region, in this cavity beneath the implant. So it was firstly empty, and then in this region, new tissue was formed. And we looked at how it's formed. Its structure in 2 weeks, 4 weeks, and 8 weeks. Okay. So I show here phosphorus and mass spectra measured after different time periods using two approaches, direct polarization, cross polarization, and we compare with references. So two references used, crystalline hydroxyapatite and mature bone from the same animal. So we can only conclude that spectra of newly formed tissues slightly shifted and strongly broadened, but not much information again. So therefore, we want to perform here two-dimensional heteronuclear correlation again. Therefore, we collected literature data, information on chemical shifts, on phosphorus, on proton, from different all possible calcium phosphate minerals. So, and this information actually is sufficient information for assigning our signals. And firstly, we'll put reference. Mature bone consists of two signals, but under assignment, we see that the signal, dominant signal, results not from hydroxyapatite, but from another calcium phosphate, octocalcium phosphate. And correlation to water or hydroxide peak at 0 ppm is explained by the fact that mineral crystal clusters or crystallites are surrounded by water and also hydroxide. The presence of hydroxyapatite is also found, but in a smaller fraction. So now we look at newly formed tissues extracted from animals, different animals. We use it, so therefore you see two rows, so just for statistical reasons. And vertical direction is a time. So we looked after 2 weeks, after 4 weeks, and 8. So what we can conclude, basically, the development of the healing time is similar. So the tissue develops and becomes, after 8 weeks, more or less similar to marriageable. That means biomineralization process has been almost completed after 8 weeks. So actually, this is expected behavior, and it happens also in human heart tissues, bones. Based on literature data we collected, we now can assign different peaks, and we find the presence of octocalcium phosphate, amorphous calcium phosphate, beta-3 calcium phosphates at the earliest stage of mineralization, and then the process of rebuilding, remodeling takes place, and we see the appearance of supposed to be restarted. Hydroxyapatite, the main heart tissue constituent, appears only 4 weeks. So this is final information from our study, and I can conclude that heteronuclear spectroscopy, heteronuclear correlation enables to identify early stages of biomineralization and can prove non-classical way of biomineralization. So we performed ex vivo NMR study of in vivo bone tissues and found that the process had been completed after 8 weeks of healing time. So now in the last part of my data presentation, I'd like to show our recent study, just recently published, in situ redox flow NMR for electrochemical reactions. So here I list the specific applications and advantages of NMR, which are quite important in the energy research field. So because we can simultaneously measure gas, liquid, and solid, which is interesting for battery application. NMR is a quantitative technique, therefore we can extract quantitative structural information. Not only structure, but also dynamics and intermolecular interactions can be plotted. So the method is non-invasive, and we can, for example, apply selective labeling to get more information about structure. As I mentioned, we can study interfaces and probe different nucleus within one sample. So this all advantages provide good background for using NMR in situ. So why in situ is so important in electrochemistry? Because if we perform the reaction, chemical reaction in chemical lab, and then transfer the sample to NMR lab, some short-living intermediate or products can be lost, and we don't get the full information and can't, for example, elucidate the reaction mechanism. Therefore, it's important to perform the reaction exactly in situ in the place of NMR setup. Here you see a common NMR setup consisting of a superconducting magnet and probe head, which contains also sample in RF coil. The probe head is connected to spectrometer and RF amplifier. And for in situ NMR, we developed an electrochemical cell, which is in addition connected to potential star. Which means we can somehow model a battery within this cell, apply electrical voltage, and measure NMR spectra during the battery operation. So, but we have extended this research to so-called in situ flow NMR setup, and in addition connected this setup to a pump and a container which contains liquid, for example, electrolyte. So the multi-functionality of this setup is as follows. So we can provide continuous flow of a liquid or electrolyte. We can apply electrical voltage and measure NMR spectra at the same time. So, and here you see schematical representation of this inflow NMR cell, which is quite small, few centimeters in length. And you see that the liquid or gas can be introduced, electrical voltage can be applied, and reaction can take place on so-called working electrode, which is used as catalysis. So this can be gold plate or copper covered gold plate. So we can also perform electrocatalytical reactions or electrochemical reactions. So, and we wanted to test this setup on some case studies. The most actual study now in electrochemistry research is electrochemical reduction of carbon dioxide, so CO2. We know that CO2 is a greenhouse gas, and once we are able to convert CO2 into value-added chemicals, so we can kill two birds. The first, so we mitigate the climate change, we make our planet cleaner, and the second, we produce value-added chemicals, which are both can be used as chemical feedstocks, so we can produce other more complex chemicals from ethanol, for example. And they can be used for energy storage. So this is another kind of energy storage, when energy is stored in chemical forms. CO2 can be converted in different substances, for example, methane, ethanol, methanol. But methane is a gas, CH4, it's volatile and dangerous to store it. It makes sense to produce liquids as precursors of fuels or as energy-dense materials. Therefore, the aim is selective electroreduction reaction towards desirable multi-carbons. So the aim is to produce material which is consisted of two carbons connected by chemical bond. The most simple, most available is ethanol. So we need, therefore, in situ characterization tool, and NMR is most suitable for this aim. So we used our setup for this kind of reaction. We dissolved CO2 gas in electrolyte, let it flow through NMR cell, applied electrical voltage, as you can see here, and measured the deuterium spectrum. Deuterium, because we used partially substituted heavy water in the electrolyte. And vertical direction of the time. So this is just set of the mass spectra collected at the different time periods. So we can extract one spectrum, deconvolute, and look at different species. And now I would like to state that this study is a proof of concept. We wanted to show that this approach is working. But to elucidate the structural information and the reaction mechanism, we need, of course, to modify this study in order to get better resolution and more quantitative information. So, but anyway, what we can see, different species can be assigned. We see different water arrangements, and the most interesting is this minor red component around 2.3 ppm. This signal can arise from different substances, from ethanol, acetic acid, any other, but they are all multi-carbon products. So they all consist of two carbons connected by chemical bond, and this was our aim, actually. So again, if we look at extracted spectra, we see that this line, highlighted by red color, appears at a certain electrical potential. So this is a clear demonstration of electrochemical reduction of carbon dioxide into value-added chemicals. So here I listed the signals which we can observe in our spectra. So, and we see that some signals identified as multi-carbon bonds. So here's the end of my presentation. It's kind of graphical summary where I wanted to show that in situ flow NMR setup can be used in order to demonstrate intermediates or reaction products during the, for example, reduction of carbon dioxide into value-added chemicals. And at the end, I'd like to thank my former colleagues from Freiberg and from Dresden, my project partners, and all of you for your attention. Thank you very much.
Okay, this talk and this material is not strictly in line of our traditional, I would say, study of condensed matter. So there are, at least for me, there are quite many unclear points which could be clarified a bit later. Might be now you have some quick questions, general questions. Okay.
Well, I have, concerning your last part, I have a general question I don't understand. You are proposing somehow to me a route to produce hydrocarbons out of CO2, but you are using electrochemical method. The energy that you put to get rid of the CO2 is it should be less, no? But the energy that you will get out then from the hydrocarbon later on, no? What I'm trying to say is that okay, to produce this, I'm using some electricity.
Yes.
The electricity is produced via has some sort of CO2 fingerprint. So is the quantity of hydrocarbon that I get from these reactions are higher or lower than the whole process? What I'm trying to say is the process, this electrochemical process, good enough to let's say release CO2 in the whole balance?
This study, not of course, and this is just proof of concept that we can observe. And this was the aim of this study, to fabricate such cell in order to find proper chemical and electrical conditions for effective and selective electroreduction. So we want to see that it works, and now we can use it to vary electrical conditions, to change electrolyte, to change concentration, and find where it works the best. This is only the beginning of our work.
Well, maybe we can discuss later, because I'm working on cements, and some of your NMR techniques are like similar in cements. You have calcium silicates instead of calcium phosphate. So it's very similar. I think if you have some time, maybe we can talk later on.
No, thank you, very nice presentation. I have a couple of questions. So, your first part of the talk, so the solid state NMR, of course, you use those materials because they have all these convenient nuclei, phosphorus, fluorine, proton, and so on and so forth. Can you do it on other type of materials? So minerals, for example, where you have metals, quadrupolar nuclei, and things like that.
In principle, yes. You mean the heteronuclear correlation?
Yeah.
It also depends on the strength of quadrupole interaction. If we are talking about quadrupole nuclei, it has been shown to work, but it's not
Straightforward.
so easy, but it can be in principle used. There are.
Do you know what type of other element or metal-based metals?
With metals, is also there is limitation on concentration, but kind of metal organic framework.
You can do it on most.
Yes. It
And
can
then another question related. I mean, your proton NMR on the collagen side was very broad, right? On the y-axis, right? Because I think there are many different protons, water inside, exchange, and so on and so forth. So, but I mean, I guess you can reduce, or improve the resolution on that side, right? In theory, I mean, can you see analytes in that phase? Imagine that I put some small molecule in the collagen side at a decently high concentration. Can you then see selectively the CP, the polarization transfer of the small molecule to the solid phase, inorganic phase, or that is too much to ask?
might be possible, but also depends on mobility.
On the okay.
If
Yeah.
they're too mobile, so it's quite difficult to transfer polarization.
Okay.
So therefore, we need really to
Something
work with condensed matter, or somehow limit mobility, or maybe to do it at low temperatures.
Maybe last question.
Mhm.
The electrochemistry part, this is very interesting. I mean, I didn't get why you looked at the deuterium resonance and not at the proton, for example. And the second question is sensitivity, because NMR suffers from sensitivity. I mean, you could do spectral electrochemistry with UVVs or infrared, and probably would give you similar information. NMR can give you structure, but you need high concentration of analyte to see the resonances.
Okay.
What's your view
The
on it?
first question was about deuterium. The reason is quite simple. We had only one channel top head.
Okay.
So, either we can measure on X nucleus or protons. So, and we decided to construct only one channel for start, excluding protons. And therefore,
Okay.
we have much more possibilities for investigations and concentrated on deuterium. So, and if we replace it spatially, heavy water to normal water is 1 to 2. So we can also reduce the homonuclear dipole coupling and reduce line width. And the second question was why NMR?
The advantages, yeah, I mean, what would give NMR compared to other, say,
As I mentioned, one of advantages is non-invasive technique. So we can provide reaction, or we can always put some starting material and let it work and measure all the time, non-stop. So this is endless experiment.
And the NMR time scale will be very different from the electrochemistry. So why putting the electrochemistry device inside the probe? I could have it outside and have the flux coming in and out.
The second additional answer that it allows not only studies of liquid component, electrolyte, but also the surface itself. I can't show here, but we also measured copper spectra. So we can measure one after another a certain voltage parameter, and it was quite interesting to observe both. So this enables to measure reaction container at surface, catalysis surface.
More questions? Yeah. Okay. Goals. Okay. Okay.
How do you know that you was you see any other ways to accomplish if so I think that's that question.
The first question was about how we can distinguish interface signals from other. And so we know the structure of inorganic component, which is pure fluorapatite, and because we have also X-ray evidence and ADX measurements, we know what is it, and so we can exclude the signals from inorganic stuff, and what we see the rest is another space, either organic or interface. But interface also we can vary this time of the magnetization transfer. If it's this time is very short, we probe only closest distances. And therefore, we can distinguish by interface close to fluorine to fluorapatite fluorine. And all the rest we can attribute to amorphous phase.
Because you know that some limits are present on that side and then
yes, it's true. It was quite complicated interplay of all signals, but if you deep in this analysis, you start to understand easily what comes from which phase. It seems very complicated, but then it looks quite unambiguously. Of synthetic bond. So the dental piece like 2-3 centimeters, and the cavity less than 1 centimeter cubic.
Okay, no questions? Yes.
Thanks a lot for the talk. It was very nice. I actually was very curious about the second side for insulin electrochemistry. I think it's really powerful that you can actually look at the products and the copper. And I wanted to ask about the copper. You were able to see some reduction, like it's to start with oxide and then follow the amount of oxide metal with this technique.
You're talking about this electron reduction?
Yeah.
On copper.
Yeah. So you mentioned that this was done with copper catalyst, right?
Yes.
And then were you able to follow things the copper with the reaction?
Here, not really.
Okay.
Because of small area. But in principle, it can be done. But we need to focus on the result and somehow modify the setup.
I see.
And the spectrum is very broad from copper, as you can suggest. Therefore, you need also specific approach, either measure by frequency or sweep width or so on. But you can expect a copper signal everywhere, far away from the center line. So therefore, it's could be challenging and time-consuming experiment. Let's see.
Okay, no questions? Okay, if not, okay, let's thank. Okay, from your name, from my name, the speaker, okay, for his nice talk. Okay, thank you very much.
I'm working on cements, cement are calcium silicate. Yes, cements are calcium silicate. This kind of cross vaporization technique.